Assalamualaikum. In this session, we are going to learn about infrared spectroscopy. Let's understand the principle of infrared spectroscopy. When electromagnetic radiation strikes a molecule, some wavelengths have been absorbed and some are not. For IR absorption, the energy of photon must equal or match with the delta E in the molecule. What is delta E in the molecule? Is the difference between higher energy state with a lower energy state for a certain molecule. Different molecules have different delta E. So in order to have a signal in infrared spectroscopy, the molecule must absorb certain energy in the IR with equal to the delta E. So the larger delta E, so means the higher energy radiation is needed for absorption. When the frequency of IR lights match with the delta E, or delta E known as vibrational mode energy, and it will have a change in the amplitude of the particular bond range, and the amplitude will be increased. Here, this is a delta E. Let's say this is a delta E for the certain molecule, and for a molecule to have a vibrational mode, they have to absorb the energy from the IR light equal to the delta E. So, and when the enough energy, it can have a bond strange further. When the frequency of IR equals to the frequency of bond range, the IR light is absorbed. Different kinds of bond vibrate at different frequencies, so they absorb different frequency IR light. So that's why in IR spectroscopy, it can distinguish between the different kind of bonds in molecules. So it is possible to determine the functional group presence. For conditions for compounds to absorb the IR, the compounds must be polar, must be unsymmetrical, and must have a dipole moment. For IR spectroscopy, it used to identify the functional group in a compound, and the IR radiation is the energy source used in the IR spectroscopy, and the frequency in IR spectroscopy are reported using unit called wave number. The symbol is here, V with a bar at above, and this formula is equal to 1 over wavelength. The wavelength is inversely proportional to the wave number, and the unit is centimeter -1, and frequency is also known as the wave number. So when the frequency increase, the wave number also increase, and the scale for the IR absorption always be within 4000 to 400 centimeter -1. So this is the basic principle for any spectroscopy. The molecule have in the rest states will have absorb enough energy from the light source or radiation source, and when they have enough energy, the molecule will goes for the excitation state, and from the excitation state they will release the energy to go for the rest state, which is called a relaxation. From this relaxation state, the signal will be detected. And in the IR spectroscopy process, because of the change of the molecule vibration, it involves two waves from the different two atoms. So the signal will become a couple wave, as shown in this figure. So next, when it involves the vibrational modes, it have two different vibrational mode changes, whether it is stretching or bending mode. The stretching, bond can stretch. When the bending is two bond can be bent, and the vibrational mode will be quantized, and so they will occur only at specific frequency, which correspond to the frequency of IR light. Let's see what is the type of stretching. It can be symmetrical or asymmetric. What is symmetric? The molecule vibrate, the atom in the molecule vibrate at the same direction, and asymmetric is the atom approach to the central atom to the other depart from it. Means two different direction. Next is the type of bending. Bending, they have four different types: scissoring, rocking, twisting, and wagging. We can see scissoring. What is scissoring? Like this, like scissor. So two atoms approach each other. Rocking, two atoms take place in the type of movement of the atom take place in the same direction, whether it can be on the left or the right for both atoms. Twisting, one of the atom move up and one move down. And wagging, we can see both atom move up and both atom move down. This is different type. Because of this different type of vibrational mode or stretching mode, they have a different frequency for each mode. If you can see, the symmetrical is 2853 and unsymmetrical become 2926. Is more higher frequency compared to the symmetrical. And the scissoring is 1450, wagging is 1350, rocking is 720, and twisting is 1250. It's a different frequency in different mode of vibrations. In order to understand more about the principle in the IR, how the frequency have been differentiated, we need to understand the Hooke law. The Hooke law is simulate the spring system where two mass of atom have been connected with a spring. Here it represents the K is the force constant. The force constant shows the bond strength, and the mass of two objects is represent the mass of the atom. This is how we can use the Hooke law to have a understanding about the FTIR frequency. So based on this formula, the Hooke law define the wave number is equal to 1 to pi c times with the root square k divided by mu. What is mu? Is the reduced mass. Based on this, we can see the wave number is directly proportional to the force constant of bond strength and directly inversely proportional to the mass. Means when the bond strength increase, the wave number increase, and when the mass is reduced, the wave number increase. So let's see the example directly to the molecule or atom. As we can see from the formula, for a bond strength increase, the larger K value, so the wave number will increase. As an example, if you can see, C single bond C is a less strength compared to C triple bond C is more strength. Bond strength increase, so the wave number keep on increasing. Same goes to the CH, which is directly bonded to the single bond, double bond, and triple bond. The frequency keep on increasing. Because of the bond strength increase, the wave number will be increased. Example number 2, which is relate to the mass. When the mass of atom is increased, so the wave number will decrease. We can see the C double bond C is the higher mass, so the wave number decrease because it's inversely proportional to the mass, the wave number. CH is more lighter, that's why the wave number is more higher compared to C, the single bond C. And here C single bond Cl, so the mass is higher, so the wave number is lower. More higher become lower number of wave number. So after understand the Hooke law with the frequency, let's go through directly for the calculation of the Hooke law. And this is the formula. Just now, wave number is equal to 1 to pi c root square with a k divided by mu. So the k constant is the force constant, or we relate with the bond strength. When the bond strength increase, double or triple bond, this value will be increased to double or triple. So c is velocity of the radiation will be given, and this one is the mass also will be given. Let's see how to calculate based on the Hooke law. Okay, so based on the Hooke law, they will give this information. Just put inside the formula, and this how it comes 7, because pi is 22/7, so 7 is picked up. So when calculate in the frequency, so how to calculate, because they are not C including here. That's why if you can directly 2 pi C can, or you can separately calculate like this. So it can be converted. The frequency can be converted to the wave number by relationship with the velocity of the light. So based on this calculation, hopefully we can get clear understanding about the Bond's range with the mass and the wave number. So here, C double bond C strange is expected to absorb a high frequency Y compared to single bond C. Why? Because C double bond C have a more bond strength, so they have a value of K constant double compared to the single bond. Same goes to the OH strength, absorb higher frequency compared to the C single bond C. It can be explained based on the smaller value of reduced mass. So OH is more light compared to the C single bond C. This one 16 plus 1 is 17. 12 plus 12 is 24. So the mass 24 compared to 70. So because of the mass is inversely proportional to the wave number. When the mass is light, the wave number is higher. That's why we explain why OH is more higher compared to the C, the single bond C. Then when we expect OH to absorb higher frequency as compared to the FH, this is not true. Actually, FH absorb higher frequency. This is because of the higher electronegativity of the fluorine compared to the oxygen. This one is related to the bond range. Although the mass is here, but the most priority is the bond range. Next, it's important to make notes the peak intensity. Rather than we understand the frequency, we also need to understand the intensity of the peak. The symbol that always be written is as, medium, weak, and broad. So strong is declared when the peak is tall and transmittance is low. And medium peak is medium high, and transmittance is in between 75 to 35. And weak is short, transmittance is high, 90 to 70, and broad is broad absorption. That's the terms that we need to understand based on the intensity, broad, medium, and strong. And the functional group, the primary use for the IR, as I mentioned before, is to detect the functional group. It looks the interaction of electromagnetic spectrum with the actual bonds. It provides unique qualitative proof for the functionality of a molecules. So different type of bonds and covalent molecules have roughly different the same energy. Let's say if we can see C double bond C, C double bond O, CH and H show the similar region in the IR spectrum. They are more basically on the type of bond. So based on this characteristic on infrared spectrum, the infrared spectrum is plot the amount of transmittance or absorbed light versus the wave number. The x-axis will be the wave number, and the y-axis is the transmittance. Always we convert into percent of transmittance, mean that all the light on the sample is transmit and none is observed. If 0% transmittance, mean all light is absorbed. Each peak corresponds to a particular kind of bond, and each bond type occurs at the characteristic frequency. Where a peak occurs is reported in centimeter -1. That's the characteristic of infrared spectrum. What is the y-axis, what is the x-axis, and what is the unit used for the frequency in the IR spectrum. So we can see the trend in the infrared spectrum is always in the region 4,000 to 400 actually. So when the divide into two regions, which is more than 1,400 and less than 1500 is called a fingerprint region. Mostly we try our best to identify the functional group more than 1500. In the functional group region is rare to be used, but it really used when you want to compare different types of the presence of auto meta para on that region. Mostly we use in the region more than 1500. And the IR absorption, as I mentioned just now, for the IR frequency, it really depends on the bond strength and the mass of the atom. So when if based on the Hooke's law formula, we can know that the wave number is directly proportional to the bond strength and inversely proportional to the atom mass. If we can see, same weight, the strong vibrate at a higher frequency. For the spring of the same strength, the spring with the lighter weight vibrate at a higher frequency. This is the sequence. If we can really understand the Hooke's law, then we can see the trend of the bond absorption in the IR spectrum is like this. When increasing wave number means the bond is here. You can see the bond is lower. Increasing the wave number. So when a bond strength increase, so the frequency increase. Then when the more light atom, it goes for the more higher frequency. We can see this region, C single bond, C double bond, C triple bond. So we keep on increasing on the based on the bond strength, and this one come in from because they are more light atom. So this is the fixed region. Before they fix this one, this is the principle of the IR with the mass of the atom and also the bond strength. So that's the basic principle of IR. Hopefully this one can be identify a different functional group of the sample and how to prepare the sample. Sometimes we always use the KBR pellet or NaCl pellet, or we can use the liquid sample by using FTIR. And this is the schematic diagram for the inside the FTIR, where the light source is infrared and they have a beam to split the light and to filter the certain frequency. And this is our sample. When the light is passed through our sample, it go for the excitation state and the light will be emitted and will be detected and cause the signal. So this is the route, how they filter the light and pass through, and that's all for infrared. Thank you.